Hello, good afternoon, happy Monday. Hope everyone had a nice weekend. Excellent. I also had a good weekend. I tried a couple of things over the weekend, one of which was to grade all of the proofs, which I think I successfully did. I gave you comments if you handed it in on Canvas. I did not give you comments if you handed it in person. I mean, I wrote them on the sheet, but I haven't given them back to you, part because I don't have permission to give them back to you. I'm going to be sending around right now to the people who are in the room a piece of paper with your name on it. If you are okay with me returning graded materials to you in the mailbox in the Modern Physics and Optics Lab in ISC 215, if you would not mind, please sign this next to your name and I will return them. Otherwise, you can just come and see me and I will give them to you in my office. I attempted to upload grades to Canvas, somewhat successfully, somewhat unsuccessfully. There is, right, so what grades do I have for you right now? It's 2 Kappa scores, and that's what I tried to do. And that went off not so well the first time. There was some minor bug that caused some people's scores to get a little bit adjusted. That's been fixed as of this morning. The other thing that happened was I didn't realize that it would upload the zeros that I have in my gradebook for participation, because I haven't asked any participation questions in class yet. That will happen at some point. We'll get out Top Hat and use it actually during the class, and then I'll keep track of it, and it'll be a small portion of your grade. But right now it's showing up as 0 for almost everybody, and that is obviously not right. So don't worry about that. That will change as soon as we start asking questions and get into that part of the class. So sorry about that confusion. Were there other questions or comments or concerns about the grades that have been posted? Okay, it's basically exactly what shows up on Kappa, should show up now on Canvas as well. I think that's it. I don't think there's any logistical things, other things we needed to do. I've got, if you have not already, it looks like everybody in here has pretty much filled the attendance thing out. I'll give you a couple more seconds to do this if you haven't already. What we got here is a slide I should have probably put up last class, showing another way to think about the inverse square law of light. If you have a point source or a source of energy that's uniformly radiating away that energy in all directions, then you will have a situation where if you follow just light through a particular cone or a particular region of space as it expands outward, you know that the area subtended by a particular region, for instance, if you are calling this 1 square area, as you move away from that source and get twice as far away, that same amount of light will be spread over a region that is 2 by 2. And if you go 3R away, it will be spread over a region that's 3 by 3. This is why you get a 1 over R squared dependence on radiation emanating from a point source. Another visual way to think about it. Okay, so that was our first example. We did an inverse square of light example. The next example that I want to do is actually on the next slide. It is this. Suppose we have a light source, and that light source is giving off some radiation at a distance away from an object. The question now is not how much total power, the question now is not what the intensity is at the mug. We know the intensity will go off as 1 over R, down as 1 over R squared. What if we want to know the total power absorbed by the mug or incident upon the mug? Okay, so that's the question, second example that we're going to be doing. And this gets a little bit tricky because we've got 2 powers to think about now. We know the power, we're often given the power that's emanated from the source, and we want a different power. How much energy per second, which is a power, is absorbed or is incident upon the mug itself. So let's do this. Power, so this is example 2. Power incident on an object. In this case, coffee mug. So we have an intensity formula. So first of all, let's say the power of the light bulb. Let's say we've got, I should have just brought a coffee mug and a light bulb. Got a light bulb over here and a coffee mug over here. We need to figure out, there's two, we're going to use the power equals intensity over area formula twice. And that's what gets a little bit confusing. So let's say the power is a 60-watt light bulb. So 60 watts of energy are leaving that bulb every second. We know, what is the intensity formula? Well, we need to first figure out what the intensity is at the mug. And the intensity at the mug, I'm going to call that IM, intensity at the mug, is the power divided by, I is always P over A, power divided by area. Okay? What is the area? If I've got a bulb here and a mug here, what area am I talking about when I talk about the intensity of the light at this mug? Good guess. The mug wouldn't even have to be there for me to answer this question. What is the intensity of this light at the distance of the mug? It could be a mug, it could be a basketball, it could be a quarter. That number is not going to change. It is how bright that light seems at this point. That's exactly right. It would be a surface area of an entire sphere centered on that light bulb, because we're spreading the power over that entire surface area of that sphere. So that's the first formula. In fact, then we wrote this formula down explicitly. P over 4 pi r squared. PS, this is, now we have to be careful, this is the source power. This is the power of our light bulb. This is I mug, and this is I source. Great. So we want the power absorbed. Now we know what the intensity is. We can use the same formula, IM equals P over A, I equals P over A, to determine now a different P, that P being the power absorbed by the mug itself. We know what intensity is now. We can plug that in and figure out what the power absorbed is, or incident upon is. Okay, so we want the power absorbed. I'm going to call that the power of mug, PM, power incident upon mug, or power absorbed by the mug if it's a perfect absorber. That is going to be, it's the same formula. It's intensity times A. But this is a different A. What is this A? The surface area exposed by the mug. Surface area exposed. But to think a little bit about that, there's a lot of different areas we could think about for this particular mug. When you say exposed, what exactly do you mean? The parts of the mug that the light's actually facing, the mug's actually facing the light, say. Okay, that's an interesting guess, and it's a great guess. It happens to be a little bit off, but not much off. And the problem is, our mug is not a perfectly square thing. We have parts of the mug that point in this direction and parts of the mug that point in this direction and parts of the mug that point not exactly in the direction of the light itself. And so, yes, there might be a square inch of surface area here, but it's not getting a full square inch of light of energy from the light because it's not pointing directly towards the light. And that makes it really complicated to think about. You'd have to probably, if you want to do this right, if there wasn't an easier way to do it, if you want to do this right, you'd have to do you could imagine a intensity vector times a surface area vector and doing some cosine or dot product of the surface integral over that whole thing. That's probably what you'd have to do, very similar to what we've been thinking about otherwise. There's a simpler way to think about this, and that is that all of the light that's incident upon the entire thing must be incident upon it and absorbed by it. So if we can think about what the cross-sectional area of this thing is, in other words, if I were to put a sheet of paper right behind that coffee mug, what would be the shape of that thing and how big would it be that was casting a shadow by that thing? All of that light must be incident upon that mug. Right? So in this case, it's some kind of cross-sectional area. The area of a shadow on a piece of paper immediately behind that mug and what that area would be. So this is in this case, A is the projected area, I will say. Of the mug itself. Does that make sense? Okay. So let's assume our mug is a cylinder. Let's assume that there's no handle poking out, so we don't have to worry about that. We've oriented the handle so it's pointed away from the light or something like that. What is the projected area of a cylinder that's perfectly in line and not tilted in some weird angle to the, I guess it depends on how you do it. It certainly depends on how you hold the thing. Thank you very much. But let's say it has the orientation that we put in this diagram. What would be the projected shape of that thing? Yeah, it's going to be a rectangle, right? It's going to be the height times the diameter. That's what we're looking for there. So this is just, let's say, diameter times height, or 2r times height, if we like. Okay, so we can plug all this stuff in. Our power incident on the mug is the intensity, which is PS over 4 pi. I'm going to call this little r squared. Little r, I should have called this little r up here too. Little r squared is the distance between the light source and the mug. And I'm going to call this h times 2 big R, which is the radius of the mug itself. You can put all this together. You get the source power times the height of the mug times the radius of the mug divided by 2 pi times the little radius. Keep getting those R's wrong. Squared. That's really all it is. It's using that P equals I equals P over A formula twice. Once you know the power and you determine the intensity, and the next time you know the intensity and you use it to determine the power absorbed. That gets a little confusing. Another way to think about this is this. Let's say we've got our light source in the middle, right? We've got, again, we're drawing some giant sphere around that light source where the intensity is spread out by. And here is our coffee mug just intersecting that sphere. How much power is incident upon that sphere, upon that mug? It is the fractional area of the entire sphere around that light bulb that is masked, that is covered, that is occupied by that mug. right? It's the fraction of the total surface. It's the incident power. It's the exit power divided by the fraction of the area that's actually being absorbed. So you could call this incident on the mug. Power incident on the mug is a source power times the area of the mug, the projected area of the mug, divided by the total area. That's not a bad way to think about this. It's really the fraction of that light that's been subtended, fraction of the sphere that's blocked by the mug itself. Okay, great. Let's move on to another topic. Why aren't I having success here? Oh, maybe because I'm using the wrong thing. Nope, it just doesn't want to go. Let's try doing it here. Okay, that worked. Okay, so this new topic is polarization. All right, if you thought the hand waving arguments were bad before, this is only going to get worse, but that's okay. There's a couple of formulas we need to know, and there's a couple of concepts that we need to know, and that's pretty much it. How many people own a pair of polarized sunglasses? Excellent. How many know what a pair of polarized sunglasses does? What does it do? Anybody? Reduces glare and what? And light bouncing off surfaces. Yeah, that's the idea. Have you ever gone out on a clear day and done one of these things and looking at the daytime sky with your polarized sunglasses? If you haven't done it, do it on a bright day. You'll notice regions of the sky going dark, and then other regions of the sky going dark as you tilt your head 90 degrees one way and 90 degrees the other day. It's kind of cool. So this is all because the daytime sky is partially polarized. So what does that mean? What do we mean by polarization? What does it mean if light is polarized? What does it mean if light is unpolarized? And how can that even happen? Okay, so far, we have been considering electromagnetic waves propagating along in the x direction, where the E field points in the y direction and the B field points in the z direction. This is polarized light. Anytime the E field always points in the same direction, the light is considered to be polarized. This is linearly polarized. We're not really going to talk about circular polarization. It's interesting, it's fascinating, and it'll be for another class. So for instance, as the wave propagates, and more importantly, as other parts of this wave reach a certain point, the electric field is always in the same, obviously the direction isn't changing, and the E field always points in the same direction. I could have very easily also said that the B field is pointing in the same direction, but if I specify one of those things, I've automatically also specified the other of those things. Okay? Okay, so interestingly, and this is where things get cool, there exist things that can change, even for a linearly polarized wave, can change the direction that the E field points in. This orientation, the direction, I mean the direction of the E field. Seen from the front, so if you're looking down this wave and it's traveling straight towards you, you might see the electric field moving straight up and down as it oscillates, as it moves towards you. And after it passes through this polarizer that we're going to call it, that E field might be pointing in a different direction. That's what polarizers do. How? What is going on? How is it possible to change the E field from one direction to a slightly different direction? The picture that I want you to have in your head is one of a kind of like a fence row, right? So if you've got a fence row, let's imagine a fence row. So let's say this picket fence looks like this. Right? And so, I'm trying to draw the pickets nice so you can see that this is a fence row. And let's say you've got incident upon this fence row, why do I keep drawing eyes? I want to draw arrows. That's what I'm looking to draw. So this thing is moving along, and I can't really draw this, but it's going right into this fence row, straight down, right? And this fence row isn't made up of fencing though. It's made up of somehow charged particles or conducting particles that are going to absorb the E field along its axis. And if all the E field gets absorbed along its axis, the only E fields that are left is the component that's parallel to the fence rows themselves. This is an absorbing medium, and it absorbs electric field, and it absorbs components of electric fields along its line of direction. So somehow conducting rods or something like that are absorbing the component of the field in the off axis. And by the off axis, I mean perpendicular to how they're lined up. So polarizers generally do this. They generally change the polarization of light by absorbing some of that light, by absorbing some of the intensity of that light. Polarizers absorb component of light. And so the E fields and the B fields, it rotates it by theta. So if let's say we have a rotate by angle theta, the E fields and B fields will both get weaker by cosine theta. So E max and B max both get smaller by cosine theta. Where theta is the angle between the incident light and the angle of the polarizers themselves. So you know that intensity is proportional to E max times B max, or proportional to E max squared, or proportional to B max squared. This must get smaller. Since both the E field and the B field are getting smaller by a factor of cosine theta, the intensity must go down by a factor of cosine squared theta. And this is Malice's law. Malice's law says that the intensity, I'm going to write the equation down. the intensity of light passing through a polarizer, and this is important, for polarized light, I naught is the incident intensity, meaning how bright the light was before it goes through the polarizer. I is the intensity exiting the polarizer. And theta is as before. Angle between the light E field, between incident and exit polarization. So if you've got some polarized light in this direction and you send it through some polarizer, let's say it's oriented in that direction, and it comes out in this direction, then this angle, the angle between, is theta. The angle between where it came in and how the polarizer itself is oriented. That is theta. Okay, now interestingly, that's not a difficult equation to deal with, but the confusing part of this is not all light is polarized. Some light is unpolarized. If I were to take my polarized sunglasses, for instance, and look directly at these lights and do whatever I wanted to do here, the intensity of them wouldn't change. And that's because the intensity coming out of these lights is unpolarized. Sometimes instead of saying unpolarized, people will say randomly polarized. So what does that mean? It means that for the light waves, again, it's as easy to understand from a photon perspective. It's not entirely at all clear what's happening with unpolarized light in the classical way we've been talking about these waves. In some way, the light that's streaming out of these lights, the waves that are streaming out of these lights in the ceiling have the electric field pointed in this direction on one crest, and the next crest a little bit different, and the next crest a little bit different. And every crest has a random orientation of where that electric field is pointing. This doesn't really work with Maxwell's equations. It's very difficult to understand how randomly polarized or unpolarized light actually physically behaves and functions in the classical sense. But we know that it does, and we can even with, once modern physics catches up with us in 1910 or 1920, we'll be able to understand and characterize this. For now, we know that it happens. We can take our word for it. So randomly polarized, what does that look like? I've got some slides. Oh, here is polarization, right? Here is the plane of oscillation. Perfectly polarized light, that E field is always bumping up and down in the same axis. Unpolarized light is not always bumping up and down on the same axis. It is random. Every wave, that E field vector is going to be pointed in a completely different direction. That's what unpolarized light looks like. So this formula that we just wrote down is only good if your incident light is polarized. If your incident light is not polarized, you cannot use that formula, because what even is theta? It's not even a sensible thing to say. The incoming light doesn't have any particular orientation. Theta is not well defined even. So what if you have unpolarized light? What does this look like? Well, for unpolarized light, I can't even spell light. I'm a terrible writer. Incident upon a polarizer, hitting a polarizer. Two things happen. One is the light becomes polarized. And the second thing is its intensity is dropped by exactly half. Why half? Yeah, that's not a bad way to think about it. Cutting off half of the wave as it comes through. But that's kind of right. But I want you to think about also some of those waves are aligned perfectly with the polarizer and aren't getting cut off at all. Some of those waves are 90 degrees to the polarizer and are getting cut off entirely. So what is it about that? How would you, if you want to calculate that half, how would you go about calculating and proving yourself that it was a half? How would you actually go about doing it? Yeah, let's make a plot of what the intensity of the output wave would be at a given different angles, right? Let's say 0 is they're perfectly lined up, right? This is just a cosine squared law, right? I'm going to draw cosine squared right now. As we go around, here is going to be pi, here's going to be 2 pi. What is this going to look like as I go from 0 to 180 degrees? What is this going to look like? Well, when they're perfectly lined up, you get 1. This is, let's say, I over I naught. It's just 1 at 0 degrees. At 180 degrees, it's also 1. This is a cosine squared. It goes down, back up, down, and back up. That's what cosine squared looks like. This is pi over 2. This is 3 pi over 2. You can see this. I've got actually 2 polarizers here. Again, this is a single polarizer. You can see, let me actually try to do this. Can I make this really big so you can see it? I don't know. Oh, I can. That's so exciting. I can't make it really big. I make this really big. I don't know. Nope, that just went to somebody else. Oh well, that didn't really work at all. Yeah, I think you're probably right. I probably have to drop screen share.
Dr. Steinhauer, we have the ability to maximize your screen or minimize your screen.
That's interesting. Okay, well, are you still seeing? Okay, well, you guys should go ahead and do that if you're on Zoom. I can now that I've stopped sharing my screen, make this really big. So I don't know if you can see this. I'm not sure it's going to work well at all. Not bad. Let me turn off the light so that it's not so bright that we're messing everything up. Anyway, okay, so hopefully you can see, but this is going to work better than this. Not bad. You can see, again, there's unpolarized light coming off the lights. It's coming through this polarizer, and this polarizer is polarizing it, and then it's heading into this camera, right? And you can see that it is dimmer. I don't know if it's a half dimmer. I'm not going to measure it, but you can imagine it's not crazy to think that it's a half. So now, once this light is actually polarized, we can use a second polarizer to actually see if that cosine squared law actually works. So I can certainly, let's see, I've got this should be the two polarizers completely lined up at 0 degrees. You can still see there's all kinds of reflections going on. As I move the second polarizer 90 degrees, it completely goes away. With unpolarized light to start with, nothing happens when I move it around. It's not polarized in any particular way. Yeah, so this is 90 degrees. Sorry, this is 0 degrees, 90 degrees, 180 degrees. It comes back again. If I can get my elbow out of the way. There we go, 180 degrees. So that's the cosine squared law. 1 at 0, 0 at 90, back to 1 again at 180 degrees. Okay, I'm gonna try to remember here to save this thing again or share my screen with you again. Oh, share screen. Oh, nice, I got a little thing there. Okay, hopefully the Zoomers are seeing my thing again. So what is a half? Well, half is just the integral of this thing over all angles, right? It's the average intensity that you get. That's where the half comes from. It's the average intensity over all those angles that are coming in randomly. Okay, great. Okay, so let's do another cool example. And this is one of my favorites of all time. So we've got these two polarizers again. And let's see if we can set them up. Here, they're perfectly aligned. Okay, I'm gonna stop sharing again. Stop share, there we go. Okay, so here we are. You can see this. So again, you've got one side, middle, other side, they're basically all lined up. It's not perfect, these aren't perfect polarizers. There's a little bit, if they were perfect polarizers and they're perfectly lined up, there would be no difference between the brightness of the wall through this one and then both of them and this one. There is a little bit of a difference, but that's really just the imperfections of these polarizers themselves. I can move them to 90 degrees and there is 0 light coming through the middle. Again, if they were perfectly polarized, perfect polarizers, they would be actually, and I got them exactly 90 degrees apart, there would be no light at all coming through the centerpiece. You can see it's not horrible. We've done a decent job of blocking all of the light coming through. Polarizers, though, set up some weird thing. This is like magic. You're gonna love this. Watch this. It turns out I've got a third polarizer here. Here's my polarizer. So let me get this back up so you can see it. I can see this coming in, right? That's pretty cool too. Look at this. Right? You see how this is perfectly in line, perfectly anti-symmetric. So you can see the same thing basically with this one and this one. But here's the cool thing. I can put this one between these two polarizers where no light is coming through at all. And if I do it in the right way, this is not the right way. This is better. You can actually see it going between them. This is not the right way, but you're not gonna be able to see the wall. How do I hold all this stuff? Here we go. Oh, well, you just have to trust me if you're zooming that this is actually going between them. So watch this. Are you ready? We're gonna look for that sign. If I move it 45 degrees, oh, that's sad. You can't even really see it. Wow, all that drama and you can't even see it. Here's the thing. I'll describe this to you. There's no good way to show this to even 30 people in the same room at the same time. It's even worse if you're trying to show it to both people in the room and people not in the room. Let's see. It's got to be a better way to do this. Nope, I'm not going to get it. Anyway, stop by my office sometime. I'll have these out and you can play with them. The cool thing is, if you have two polarizers that are 90 degrees away from each other, and you put a third one in there that is, say, 45 degrees from both of them, what was normally no light getting through, you can put something else in between them, and now light gets through. Right? It's like magic, even if I can't actually show you up in the front of the classroom. Okay. So we'll do an example that includes that one in a sec. Let's do some polarization examples. So let's do some example. Let's do some calculation examples. Unpolarized light whose intensity is, let's say, 10 watts per square meter, passes through two polarizers. Here we go. Actually, three polarizers. I don't know why I wrote two. I actually have three here. Okay, so here is intensity. You've got some incident unpolarized light. Let's say, this is how I'm gonna draw my polarizer, and I'm gonna represent the angle by imagining the charged rods in the circles. So here is I naught, obviously coming here. We've got I1, this is polarizer 1. We've got I2, and let's say that this angle is 20 degrees. Through, this is 1, this is 2. Through polarizer 3, this angle, let's say, is 50 degrees. I've drawn them about the same, but let's assume they're different. Okay, so the question is, we've got I0, I1, I2, and I3. The question is, how much light is exiting the third polarizer? What is the intensity of the light as it exits the third polarizer? So we've got some orientation for the first one. The second one is 20 degrees shifted from the first polarizer. The third one is shifted 50 degrees from the first polarizer. Okay, so we know that I1, in terms of let me shift this up so you can actually see it while we do this problem. What is I1 in terms of I naught? It's half. Unpolarized light passing through a polarizer, it doesn't matter what the angle is, it's always a half. Okay, great. What is I2 in terms of I1? I1 times cosine squared of 20 degrees. That's exactly right. What is I3 in terms of I2? There's a cosine squared. I'm not gonna. What is the angle? It is 30 degrees. It is not 50 degrees. It is the angle between what the incoming light is polarized at and the angle of the next polarizer, the polarizer itself. This light not only has been reduced by a factor of cosine 20 degrees in coming through this polarizer, it has also changed the polarization of the light. And so the I2 has a polarization angle of 20 degrees compared to I1, and that is the angle that matters when you're comparing to this 50 degrees. So it's really 50 minus 20. which is 30. So we can put all that together. I3, which is what we really want to know, is I1, which is 1/2 I naught, times cosine squared 20 degrees. All of this is I2 times cosine squared of 30 degrees. And if you plug all that stuff in, you get 0.33 times I naught. And if you want to plug in your numbers, you get 3.3 watts per square meter. Now, interestingly, what if we swap the second and third polarizer? What if instead of going 0, 20, 50, it goes 0, 50, 20? Will the I naught be, will I3 be the same? The answer is no. The order actually matters here, right? If we swap 2 and 3, what are we going to get? I3 equals, we still have 1/2 I naught. We still have a cosine squared, but the first cosine squared will be 50 degrees. And the second cosine squared will be 20 degrees. Sorry, 30 degrees. And that is a very different number because the cosine squared of 50 degrees is way smaller than the cosine squared of 20 degrees. This will be much less light out of this particular case than the first case. This is something like 1.6 watts per square meter, half. And the output polarization angle is different than it was in the first case. So this light is less intense and has a different polarization output angle than the first example. Okay, let's do the example that we did or tried to do, right? Let's have I1 this way and have I2 90 degrees away, right? So this is some incident I naught, some I1, and some I2. This is easy. If this angle is 90 degrees, then I2 is I1 times cosine of squared of 90 degrees. And that's 0. No light should come through. But what if we put another polarizer in between them? Then we've got this situation and this situation where this is a 45-degree angle. And then our last polarizer where this is a right angle. What do we have now? We've got, we don't really care about I naught. There's I1 and there's I2 and there's I3. I3, we've got the 1/2 from the I naught times cosine squared of 45 degrees times cosine squared of 45 degrees. And neither one of those are 0 because we changed the polarization between this polarizer and this polarizer. It's no longer the case that all of those electric fields are absorbed by that one when it gets to that one. And so this comes out to be something like 1/2 times 1/2 times 1/2, which is 1/8 I naught, which is, in fact, not 0, which is interesting. So again, 2 polarizers that are blocking everything, you can put a third polarizer right in between them, and have it block everything. Have some of the light actually then go through. Kind of a cool situation. You'll do a lab on this in optics lab. And you've got almost everything you need to do the homework this week. The last question's kind of confusing, and it involves, but it really only involves, the last couple questions involve thinking about how wavelengths change in medium and how changing frequencies and how changing wavelengths are related. I will say that there's a couple of formulas that are useful to you. Maybe I'll send out an email this afternoon telling you what those formulas are. We'll definitely go over more of this on Wednesday. But those are the only two problems that we haven't really talked about yet for this week's homework. Everything else you should be able to do. Oh, yeah. Thanks.